Let us begin our journey into the fascinating world of Kolmogorov complexity, also known as algorithmic information theory. Kolmogorov complexity deals with the idea that the shortest description of an object determines its complexity. In simple terms, it provides a way to measure how complex an object is based on the length of the shortest computer program that can describe it. Here is the formal definition. The Kolmogorov complexity, represented as k of x of a string x, is the length of the shortest program that outputs x. In mathematical notation, k of x equals the minimum of the absolute value of p, such that u of p equals x. Here, p represents the program, u represents a universal computer, and x is the output string. The absolute value of p signifies the length of the program. This means that the Kolmogorov complexity of a string is the length of the shortest program that, when run on a universal computer, produces that string as its output. Let's look at a couple of examples to understand this better. First, we have a string of 12 zeros, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. This string has low complexity because we can describe it simply as 12 zeros. The Kolmogorov complexity k of x is small. On the other hand, consider a string of ones and zeros like 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1. This string has no obvious pattern and it will have high complexity. The Kolmogorov complexity k of x is large. A key theorem in Kolmogorov complexity is the Incomputability Theorem. It states that Kolmogorov complexity is not computable, meaning there exists no algorithm that can compute the Kolmogorov complexity for all strings. The basic idea behind the proof of this theorem is Berry's paradox. Berry's paradox can be stated as shortest description longer than this sentence. Now let's understand the concept of algorithmic randomness. A string is considered algorithmically random if its Kolmogorov complexity is close to its length. That is, there is no significantly shorter program than the string itself that can produce the string. We can express this mathematically as k of x is greater than or equal to the absolute value of x minus c. Here, k of x is the Kolmogorov complexity of the string x, and c is some constant. So, a string is random if it cannot be compressed much. The Invariance Theorem gives Kolmogorov complexity a robust and universal property. It essentially states that the Kolmogorov complexity of a string is independent of the choice of the universal computer. For any two universal computers, U1 and U2, their complexity measures differ by at most a constant c. This can be written as the absolute value of k subscript U1 of x minus k subscript U2 of x is less than or equal to c. This theorem assures us that Kolmogorov complexity is a fundamental property of the string itself, rather than an artifact of the particular computer used to measure it. Kolmogorov complexity has numerous applications across various fields. In data compression, it provides the theoretical limits of lossless compression. In machine learning, it is used for model selection via the minimum description length principle. It also aids in scientific discovery by helping to find simple patterns in complex data. And finally, it plays a role in bioinformatics by assisting in the analysis of genetic sequences for patterns. In conclusion, it's important to remember that complexity, in the context of Kolmogorov complexity, is about the shortest description and not just about apparent randomness. Kolmogorov complexity bridges computation, information theory, and the philosophy of randomness, providing a powerful framework for understanding and measuring complexity in various domains. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.